Inside this small vial is not a drug in the traditional sense. It's not a weakened virus. It's not a piece of a pathogen. Inside this vial is a set of instructions, genetic instructions written in RNA, wrapped in a microscopic lipid shell designed to enter your cells and exist there only briefly. Your cells read these instructions. They build a protein. Your immune system sees that protein, recognizes it as foreign, and learns how to defend against it. That's it. That's mRNA vaccine technology. By early 2023, more than 13 billion doses had been administered worldwide. It became the backbone of the global response to COVID-19. It saved millions of lives. And yet, the technology behind it wasn't new. It wasn't invented during the pandemic. It wasn't rushed together in a moment of crisis. It was the result of decades of work by a scientist most people had never heard of. Her name is Katalin Karikó, and the reason you didn't know her name until very recently tells you something important about how real scientific breakthroughs actually happen. Katalin Karikó was born in 1955 in a small town in rural Hungary. Her family didn't have running water. Her father was a butcher. Her mother kept the accounts. There was no grand plan for her to become a scientist. But she was curious. She studied biology, then biochemistry, and by her 20s, she was working with RNA, a molecule most scientists didn't find very exciting. At the time, molecular biology was obsessed with DNA. DNA was stable, permanent, the blueprint of life. RNA, by contrast, was fragile and temporary. It carried instructions from DNA to the cell's protein factories and then disappeared. Most researchers saw RNA as unimportant. Karikó saw potential. She asked a simple question: what if you could use RNA itself as a therapy? Instead of permanently altering DNA, what if you could temporarily instruct cells to make exactly the protein you wanted? The cell would do the work. The RNA would degrade naturally. No permanent genetic changes. It was an elegant idea, and almost no one believed it would work. In the mid-1980s, research funding in Hungary collapsed. Karikó had a young daughter. Her lab could no longer pay her, so she and her husband made a decision. They sold their car, took the money they were allowed to leave with, about $1,200, and hid it inside their daughter's teddy bear. Then they left for the United States. In America, Karikó found lab work, temporary positions, low pay, no job security. But she kept working on RNA. She proposed using messenger RNA to treat diseases, train the immune system, even fight cancer. On paper, it made sense. In reality, it kept failing. Every time synthetic RNA entered cells, the immune system panicked. Cells treated it like a viral invasion. Inflammation exploded. The therapy failed. Grant after grant was rejected. She was told her work lacked promise, that RNA was too unstable, that she should switch fields. In 1995, she was demoted, removed from the tenure track, her salary cut. Most people would have quit. She didn't. In 1997, she met an immunologist named Drew Weissman. They started talking. They realized they were stuck on the same problem. How do you get cells to accept RNA without triggering a massive immune response? The answer turned out to be subtle. RNA in nature is impure. Cells chemically modify it. One tiny modification stood out, replacing one nucleotide, uridine, with a nearly identical molecule called pseudoridine. The difference is microscopic, one bond. But when Karikó and Weissman made that substitution, something remarkable happened. The immune system stopped overreacting. Cells read the RNA. They produced the protein. Inflammation dropped dramatically. It worked. In 2005, they published their findings. Almost no one noticed. The paper didn't go viral. It didn't generate excitement. Funding still didn't come. But the foundation was laid. Years later, small biotech companies started paying attention. BioNTech in Germany, Moderna in the United States. They understood what most people had missed. Modified mRNA wasn't just possible, it was powerful. By 2019, the technology was ready, and then a new virus appeared. Within days of the SARS-CoV-2 genetic sequence being published, mRNA vaccines were designed. No need to grow viruses, no need to weaken them, just instructions, wrapped, delivered, read. Clinical trials followed, results were astonishing. By the end of 2021, billions were vaccinated. An estimated 20 million lives were saved. And inside every dose was a discovery made by someone who had spent decades being ignored. When the world celebrated the vaccines, it celebrated companies, executives, logistics, stock prices. Corico's name barely appeared, not because of a conspiracy, but because science rarely rewards persistence quietly. Eventually, recognition came, major awards, global honors, and in 2023, the Nobel Prize. 40 years after she began working on RNA, when asked how she endured decades of rejection, Carico said something simple. I wasn't doing this for recognition. I just wanted to see if it could work. That's the part of the story most people miss. Breakthroughs don't usually come from genius moments. They come from people who refuse to let go of good questions. People who keep working when no one is watching. mRNA technology is now being tested for cancer, for genetic diseases, for future pandemics, and it exists because one scientist kept showing up, not because she was certain, but because she was curious. Her name is Catalin Carico. You've benefited from her work, and now, finally, you know her name.